What I'm going to talk about today is a project that's very much ongoing. That's joint with Slava Krushkal, who's my postdoc mentor, and Yangxiao, who is his student, his graduate student, who is on the job market, so you should hire him. I guess I'm also on the job market, so you should hire me too. So yeah, like I said, this is a work in progress, and it's also fairly technical. So it's an inherently challenging thing to talk about. But that being said, what I want you to get from this, so I won't talk about any proofs, but what I want you to be able to do is to, preprint is forthcoming, but I want you to be able to walk out of the room and be able to look at the preprint and get something out of it. So I kind of want to give you an overall bird's eye view of what we're doing, what the motivation is, and see how much we can discuss in 50 minutes. So yeah, anything else? No, okay, great. Okay, so first we'll start with an overview, and then we'll kind of slowly circle in and get some more details. I don't have to tell this audience, but great progress in smooth four-manifold topology has been made in the last 40 years with the use of analytic tools such as gauge theory and floor theory, but a lot remains to be figured out. For instance, the smooth four-dimensional Poincare conjecture. So there's kind of an interest in maybe constructing new types, fundamentally different types of invariants to chip away at these problems that we still don't know the answers to. And so one kind of proposal is in 2019, Morrison-Walker-Wedrich came up with the Skein Lasagna module as kind of a new, not analytic in nature way to get invariants. I won't really talk about this at all, but it's a part of a larger framework that they developed. It's the 0th degree of this thing they call blob homology. Or actually, I can't remember if they're responsible for that, or I can't remember. Sorry, not to misattribute anything. But the idea behind this is basically, what if we could do Khovanov homology in 4D? So probably we all know in this room, Khovanov homology has been a very successful a very successful way of doing things with knots and in 3 dimensions. And it's what if we could extend this framework to the 4th dimension? There's a little asterisk there because really we're going to be using Khovanov-Rozansky homology, which is slightly different. But anyway, the basic idea is the same. And this is kind of somehow fundamentally combinatorial in nature rather than analytic. So that's the overview. Sorry, I feel like I'm forgetting something, but I don't think I am. Okay, so Skein Lasagna module. On the one hand, like all good things in life, it's powerful, but it's hard to calculate. So one reason for saying it's powerful is the following preprint by Ren-Willis that people are very excited about that came out last year. So they used this invariance coming from the Skein Lasagna module theory to detect exotic compact four manifolds without the use of analysis. Actually, out of curiosity, is anyone in this room a gauge theorist? Does anyone call themselves a gauge theorist? Gordon? Well, so all right. Don't tell him I said this, but I originally said very powerful on here, but Slava said I should say powerful because I might offend the gauge theorists who, quote unquote, prove exotic results for breakfast. So not to offend anyone, it's just powerful, not very powerful. But anyway, and then I saw there's a preprint that landed on the archive today that maybe adds to this. I haven't looked at it super closely, but maybe adds to this evidence for powerfulness. I think they're detecting exotic stuff, and they do a Khovanov homology not using Skein Lasagna module stuff version, and then a Skein Lasagna version. So maybe that fits into here, but haven't looked at that super closely yet. But anyway, so there's hope that this is going to be a nice tool, but it's very hard to calculate. So here are the examples for which we can do calculations. We could do B4, and this is baked into the definition. So this is from the original paper, and I'll say more about that later. We can do S4, and notice that's not even in the original paper. So that's a paper in 2020, Manilescu-Nathalov. And this is a really, so they don't just do this. They do lots of things, and in particular, they come up with a really nice calculation technique that one consequence is you can do the calculation for S4, but you can also do many partial calculations. And this is kind of one of the only ways we have to calculate stuff is like the methods they developed here. And we can do S2 cross S2. So in 2024, Sullivan and Zhang came out with a paper that did that. And then in Ren-Willis, the same paper I mentioned on the other half of the screen, they have a generalization of that, which I'm not fully stating, but you can calculate, this result falls out of it, and it's like sum, not traces. But end list, that's it. That's all we know. That's all we can fully do so far. So it would be really great if we could do more.
So which is the compact exotic detection?
Like what are the?
What did they detect?
Yeah, sorry. So the question is, what did they detect on the left side? And I'm actually forgetting exactly what it is. It's an example that was originally known due to Akbalut. And I'm forgetting what I think it is sum, not trace, but I'm forgetting what the example was. I said I think it's sum, not trace, but I forget what the example is. Does anyone know off the top of their heads? Apologies. Oh, it is, yes, it's a four-manifold boundary. Sorry, was that your question? Yes, sorry. But I forget exactly what the example is. But yeah, any other questions? Okay, so a lot of the existing calculation techniques, in particular this technique with Manilisco and Nathoff, use handle decompositions or attachments. So like in what they do, for instance, their main result is they show if I attach a 2 handle, here's how the Skein Lasagna module changes. It changes in like some really nice way that we can relate, the way it changes to some other type of thing that we do know how to calculate. So that was like very successful. So our idea for our project is, well, what if we cut and paste in a different way via trisections, and maybe we can come up with some ways to calculate other things that we haven't been able to do yet. And it has come to my attention that possibly nobody has actually defined a trisection yet. I think maybe Sam did it, but apparently during the school on trisections, no one talked about trisections. So you don't really need to have like a deep understanding of what this is for the purpose of this talk, but I'll say it now, just to, I don't know, spare people talking after me having to do it. So a trisection is a decomposition of a 4-manifold into 3 nice pieces, where each of the pieces are 4-dimensional one-handle bodies, which are these things, these boundary connect sums of k copies of S1 cross B3. The intersection of 2 of these pieces are 3-dimensional handle bodies, and the triple intersection is a genus G surface. So in other words, the intersections are very nice, and kind of all of the information of the 4-manifold ends up getting encoded in these intersections. One thing to point out about this picture, which of these means laser pointer? I'm afraid to press something. All right, I won't do that, but I'll just motion. I'm afraid if I push one of these, it'll do something I don't want it to do. But okay, well, press it for a while. That's okay. That's okay. It's fine. I'll point. So all I wanted to say is that this diagram here, we use this a lot as a schematic just to like visualize what the intersections are. But something important to point out that is actually going to be very important for the rest of this talk is that this is really a schematic in the sense that these are for, what I'm describing here is a 4-manifold without boundary. And my picture looks like it has boundary. It has this like circle on the outside, but that's not actually representing a boundary of the 4-manifold. And this is going to be important later because I'm going to be talking about these pieces. Well, actually, I'll do that right now. So notice these 3 pieces. These are cornered 4-manifolds. And so I'll be drawing schematics of these like cornered pieces, but that curved part is not actually a boundary. The boundary is what's orange in this picture here, so that'll be important to remember. But anyway, the point I was getting to is these pieces are cornered. So if we want to do Skein Lasagna stuff in this setting, we need to have a framework of how to do this for cornered 4-manifolds. So that's kind of the main like focus of our project. So here's what we've done and what we've mostly written up and should be arriving in an upcoming preprint soon. So we developed a categorical framework. We define this cornered version of a Skein Lasagna invariant, and then we have two gluing theorems that say like what happens to this invariant when I glue stuff together. So the first one is if I glue two pieces along some common boundary, and then we have two, I'll explain later why I'm breaking that up, where we self-glue. And these gluing theorems are mirroring the process of building a trisection by sticking three pieces together and then gluing it together. And I'll just note, like throughout this talk, I'll just talk about as if I'm gluing together trisection pieces, but nothing about what we're doing is specific to trisection pieces. Like the pieces don't actually have to be the manifolds that I said on the last slide. So everything is stated more generally in our upcoming preprint, but this is kind of the prime motivation. So what we don't have yet, unfortunately, is kind of the punchline that we want to work towards, which is we don't have a concrete calculation. So that's the motivation, and that's what we're about to work on right now. But we've started writing this up because, you know, two of us are on the job market, and apparently it's important to have results. So, no, so anyway, but yeah, this is very much in progress. Okay, so that's like the bird's eye overview of what this project is and the motivation. Any questions about that so far before we start to dive into some details? Okay, cool. All right, let's talk about lasagnas. So, so for these Skein Lasagna modules, it takes as input some kind of link homology theory, oftentimes this Khovanov-Rozansky homology, which I'll denote this KHR. Really, there's supposed to be an N there because really this is a family of homologies where you have, it's really supposed to be GLN. Khovanov-Rozansky homology, as you vary N, you get different ones. But I'm just going to suppress that. But the typical thing is, no, I'm not going to say that. Yeah, so I'm going to, this is happening in the background, but not going to be like immediately relevant for anything I'm talking about. Anyway, this is a generalization. Maybe even generalization is not the right word, but kind of an extension of Khovanov homology, where it's functorial with respect to links in S3 and link cobordisms in S3 cross I. And so that's what we're inputting into this theory. Okay, so definition, if you have a pair XL, where X is a four manifold and L is a link in the boundary of my four manifold, a lasagna filling is, we'll call it F, but it's all this stuff, S, and then these collections, BI, LI, VI, where those are the following. Oh yeah, I was going to say, sorry, one thing I'll say really quickly on terminology. So these are called lasagnas, which on the one hand is funny, but on the other hand is a little misleading, I think, for two reasons. One reason is that I think typically when you eat lasagna, the components of your lasagnas are the same dimension, but that is not going to be the case here. And I think the other thing is that lasagnas don't usually have meatballs, but these lasagnas will. So take that for what you will. Okay, so the meatballs in this sense are these BI, this collection of BI, which are disjoint floor balls that are embedded in the interior of my manifold, and we call these input balls. And then we have, for each BI, we have LI, which is a link in its boundary. And then for each of these links, we have these VIs, which is an element of this Khovanov-Rozansky homology called a label. So that's the sense in which this is an input, and we're like keeping track of these labels. This is not going to be at the forefront for most of what I'm talking about today, but this would be when we try to actually do some calculations. And then tying this all together is the thing that is, I guess, the noodles of the lasagna, which is a surface, which I'll call S. Which is an oriented surface properly embedded in this four manifold where it intersects the boundary at L, and it intersects the boundary of my input balls at these links Li. So here's a picture of this. Yeah, so I'll just pause there for a second. Let everyone look at that. Any questions? Mm-hmm. Should you mean the colors of my meatball and lasagna versus that? Yes. That I did not color code those. You're right. They should be switched. Yeah, above I drew it because I was like, meatballs are orange and noodles are yellow. But here I wanted to emphasize, I didn't think about that at all. But you're right. No, but maybe someone else was confused about that. Yeah. Yeah, any other questions? Uh-huh.
So do you have a restriction on the boundary of X4?
No, it can be whatever. Yeah. But yeah, the point is that we're keeping track of, so we have these VIs, and the boundary of these balls are all going to be like S3s, and there we know how to calculate this Khovanov-Rozansky homology, and so that it's okay that the boundary of X4 is whatever. We're compensating for it in this other way. Mm-hmm.
Any element can be, of the homology can be a label, or are there like specific, like if there were a restriction on the labels?
And sorry, I keep forgetting to repeat the question. The question is there a restriction on the labels? So this might be venturing outside of what my comfort zone is, because I haven't been doing so many concrete calculations, but it's just whatever the calculation of the Khovanov-Rozansky homology of that link in the S3 is.
Oh, okay, so it's like determined.
Yeah.
Okay, okay.
Okay, but yeah, I'm not, so as you will see, we're kind of, what we've been doing so far is kind of like a pie in the sky. We've been, we know these labels exist and they're very important, but for what we're doing, we're not gonna, we're kind of working at a too high of an organizational level to worry about these right now. Okay, so now let's see what the Skein Lasagna module is. So yeah, really this is it's associated to a pair, a four manifold along with a link in its boundary. And it's this Z module generated by the lasagna fillings of this pair. And it's bi-graded, but I won't say what the grading is, but it comes from this Khovanov-Rozansky stuff. Modulo this relation, which is generated by linear combinations of lasagna fillings, are set to be multilinear in these labels. And then we have this input ball relation. So on the left-hand side, that's the picture I had earlier. So there I have two input balls, two links in my input balls, and then the labels, which I didn't draw. And then what you're allowed to do is you're allowed to take input balls and encircle them with a bigger input ball and trade the ones inside for the big one outside. So instead of B1 and B2, I'm going to trade that for this B prime, which is encircling both of those. And now instead of L1 and L2, I have this L prime, and I'll have some new label on that. And the reason, and vice versa, of course, but kind of the reason for this is that, like, if I take a closer look at what's happening in that ball, I have this like cobordism between this L dat prime and the L1 and L2. And because of this functoriality of this Khovanov-Rozansky stuff, this induces some map, and so the labels are changing in a very controlled way. And so that's where all of this comes from. So we're modding out. Anytime you can always encircle these balls with this bigger ball. And that's it. But it turns out that this implies you also mod out by like isotoping your balls, but isotoping the surface. It turns out to come from here, but yeah. Okay. Oh yeah, and then right. So when your manifold is just B4. The lasagna module recovers the Khovanov-Rozansky homology of the link. And I think the idea, I think really in order to understand this, like I would have to actually tell you about this Khovanov-Rozansky homology and what happens with cobordisms and blah, blah, blah. But I think like the basic idea is that because of this relation, like just take the B4, which is your four manifold, and just make that an input ball. And that's kind of basically what's going on here. So it's kind of baked into the definition that that's what it is when your four manifold is B4. Mm-hmm.
Can you tell more about the grading, by grading?
The question is, can I say more about the grading? And the answer is no. Not off the top of my head. It's some expression, and it comes from this grading that's part of the Khovanov-Rozansky homology, but I don't remember what this is off the top of my head. So. sorry. Like there's a quantum part and a homological part, which sounds familiar if you've done Khovanov-Rozansky stuff before, but yeah, sorry. Okay, cool. I'm also like totally unsure if, I'm trying not to blow through this really fast, so I've given one version of this talk before and I was writing on the board, so it went very slowly. So I was like, okay, I should make slides, but now I'm trying not to like rush through all of this. So yeah, please slow me down with more questions, but I'm a little unsure. We'll see what time this ends. But anyway, I think this part will go slow, so that'll be good.
Sure, you can back one slide.
Yeah,
Does this give the Khovanov, I forgot the R name,
Rozansky.
Rozansky homology only when X is before, or?
Oh, well, I guess I don't know for sure. Like, okay, a priori, I don't know because I gave you the full list where we can calculate it. But maybe there is some reason that you wouldn't expect this to happen for anything. I mean, yeah, probably this only happens in this case, but I don't know. Yeah. Okay. So now we'll actually talk about what we did. So kind of as I said earlier, so first we set up this whole categorical framework to kind of organize everything we're doing. So here I'm going to start, oh, that really doesn't look like a 3. Sorry, that's a 3, that's a Y3. So we're starting with a 3 manifold that has a boundary sigma, which is, oh, I didn't write this down, but I want sigma to be a closed oriented surface. And it's going to have a fixed set of points inside sigma that I'm going to, so I'll have some amount of points, and those are going to stay fixed for now. And so given this type of thing, I'm going to associate to it a 3 manifold category that I'll call S, Y, comma, P. So that is the same notation we use for Skein Lasagna module, but you're supposed to know which one it is based on what the inputs are. So if your input is a 4 manifold thing, we're talking about the Skein Lasagna. If it's a 3 manifold thing, I'm talking about this category that I'm about to build for you. So the objects of this category are tangles T, which are properly embedded in my 3 manifold, where the boundary of T is these points, these fixed points. So we have all sorts of possible tangles we could have, given a set of points. And then morphisms, so between two different tangles, a morphism is going to be this Skein Lasagna module of Y cross I, which is, so now we're in a 4 manifold, comma link, where the link, it's basically the union of these two tangles, but why does it look like that? So here's a schematic of, so the kind of half disk part is Y, and then the up and down direction is I. So I have one tangle in my like bottom copy of Y, and then I have one tangle in my top copy of Y, and then to connect them together, I need to do P cross I. And so then when I do that, I get a link. And so the Skein Lasagna module of this 4 manifold that I get with that link in the boundary is going to be the morphisms of between T and T prime. Oh, yeah, sorry.
These tangles are not necessarily boundary parallel?
No, yeah, so that's a great, yeah, I should have said that out loud. That's what, and I drew I drew that specifically for this crowd. So a priori, we're not requiring that our tangles be trivial, but once we do that, that'll be something that later we might restrict to. But right now, any tangles, yeah, yeah.
So I noticed that already you have a 4 manifold with corners.
Yeah.
Is that something I should worry about yet, or?
So the question is that Dave's worried about corners, and yes and no, because what I'm about to do, I'm about to have a 4 manifold with 2 of these things as its boundary, and I'm going to build something from this. So it's both a good and a bad. It's a good thing because, yeah.
So are you going to collapse this interval piece to get the manifold with corners?
Oh, no. So the question is, am I going to collapse this integral piece to get something with corners? No. Yes.
I mean, the integral cross
Yeah, right. Yeah, well, yes and no. Maybe we'll come back to that question in a few slides. Yeah. Yeah, let's put a pin in that for now. So yeah, let me say, so right, what we're doing, so we're doing this part because we need it to do this, which is what we really care about. So given a cornered four-manifold, we're going to describe to it what we're going to call a cornered Skein Lasagna invariant. But yeah, so I want specifically a four-manifold that has boundary y1 and y2, where those have boundary sigma, and I have my point set in sigma. So these y1s and y2s satisfy the structure that I had in the last slide. So and in other words, you should think of this, it doesn't have to be this, but you could think of it as a piece of a trisection. So right, yeah, again, just that curved part, not a boundary. Okay, so to this, I'm going to associate a cornered Skein Lasagna bimodule. This is going to be a bifunctor, f of x sub p, and it's going to go from this three-manifold category associated to y1 cross the three-manifold category associated to y2 to this v, which is the category of Z2 graded. I should have just said Z modules. I keep changing what I'm calling this, but the point is we're going to be mapping to Skein Lasagna modules, so we're going to land in something that is a collection of these things. So it's the category of Z2 graded, you think vector spaces or Z modules. So on objects, let's see what happens. If I input tangle 1 and tangle 2, then what I get is I should have put little definition ... thingies, but I get the Skein Lasagna module of x, comma T1, T2, that's the link I'm looking at, where T1, T2 are a link in the boundary of x. And morphisms act by concatenating lasagna fillings. And that's right, I thought I had a picture. Okay, so here's the picture. So this is like a for lack of a better word, three-dimensional version of that picture up there. I'll try to explain carefully when I'm doing this, but my pictures are going to go up and down in dimension based on how much detail I need about the smallest dimensional thing. So here's a slightly higher dimensional picture just to maybe give you a better idea of what's going on. So I have my four-manifold x bounded by this y1 and this y2, and then there's the sigma in the middle, and I have a tangle in y1 and a tangle in y2. And then I'm looking at lasagna fillings of sorry, there's a bug, of the link which is made out of those two tangles together. So the question is, to make the definition, I smooth the corners, but no, we haven't smoothed any corners. Oh, it's okay. Okay, hold on. That's fine. But the point is that we want to track, the point is if I have a Skein Lasagna of two of these things and I glue it together, I want to be able to track what's changing there. Yeah, okay, I see what you mean. Then yes, yeah. So okay, by definition, I'm taking the Skein Lasagna module of the four-manifold. That is, I smooth this corner so its boundary is y1 union y2. Okay, cool. So, okay, so kind of moving on. So that's all the setup, and then moving on to kind of the first of our results is this gluing result. So in order to, so now I'm taking two of these things, and so one of them has boundary y1, y2. One has boundary y2, y3. I'm gluing them along their common boundary. There's all sorts of stuff about orientation and picking diffeomorphisms that I'm totally suppressing because it would be terrible, but it's there, don't worry. So in order to state this, we define this tensor product. So I have this cornered invariant, which is this bifunctor associated to each piece. So this fx1, fx2. And I'm going to define what it means to take the tensor product of these things. So the tensor product is happening over this 3-manifold category of y2. And so this maps from the 3-manifold category associated to y1 across the 3-manifold category associated to y2 to V, this category of Z modules. And here's what happens on objects. So don't panic, we'll talk about it. So if I input, if I have T prime, which is going to be in y1, there should be a picture incoming. T triple prime, which is in y3. Then what happens, I take a massive direct sum over all possible T double prime that could be in y2. And then I take the honest tensor product of these two things. And remember, these two things are these Skein Lasagna modules, like by definition. So I'm taking this tensor product of these things over Z. And then I'm modding out by a relation, which I'll discuss in a second. But yeah, there we go. So here's the like 3D version of what's supposed to be happening here. So I have, there's my piece x1, there's my piece x2. I'm gluing them together along y2. And you should think of it like I'm fixing, I have this T prime in y1 and this T triple prime in y3. But I'm summing over all possible T double prime where I could glue them together and looking at different, we'll see we're going to be looking at different fillings that we get from that. So that's where everything lives. Any questions about that? I just want to pause so we can all look at this.
Strikes me as a hardly infinite sum.
Yeah. Yeah. And so that's going to be one of the main difficulties going forward that we're pretending doesn't exist right now.
The equivalent, the modding out, doesn't help that problem.
Yeah, not really. It won't. Maybe it'll help a little. I don't know. But yeah, it's not. Yeah, no. Yeah. So what are we modding out by? So what we're about to do here is something that shows up in a lot of these papers that have come before. So it's like we're defining this tensor product, and we're going to mod out by exactly what we need to mod out to make the theorem I'm about to state in a few minutes true. So here's the relation. So I'm going to first, and there will be a picture coming. So first, I'm just pointing out this A, C, and beta, these are all lasagnas. So A and C are in these lasagna modules, and beta is going to be in this morphism set. And when I write the dot, I'm talking about the morphism acting on this thing. And so here's the schematic. So now I'm back down a dimension, which is a little misleading. So the points are tangles, and the things that the arcs are surfaces. They're lasagnas. And basically the idea, so I'll come back to the notation in a second, but the idea of what's happening is that so if I have my two pieces x1 and x2, I could act by this morphism on either side, on either piece. So I could do this on the top piece, or I could do it on the bottom piece. So this, that's what this shaded thing is. It's a y2 cross I. And I could have some morphism between some tangle T tilde double prime and T double prime. And I could stick that on to x1, or I could stick it on to x2. But the point is that once I glue, it shouldn't matter which one I did. So we need to add in some relation to kind of account for this. So that's what's happening here. So A is in the Skein Lasagna module of x1, going between like T prime and some T tilde double prime. And then C is in the Skein Lasagna module of x2, going between T double prime and T triple prime. And then we have this morphism between T tilde double prime and T double prime. Okay, so here's our theorem, is that the map from this tensor products that we defined, where there's this relation. It's not written in the notation, but on the left-hand side, there's that relation encoded in there. 2, this invariant f sub x1 union x2, which is just the Skein Lasagna module of x1 union x2, is an isomorphism. So I think there's a picture. Yeah, so what I have written up there, that I just rewrote the statement of the theorem. This notation is a little bad, but so with the yellow, I was just trying to put what tangles I'm inputting into the Skein Lasagna modules. But it's a little bad because you should really think of it as like T prime and T triple prime are like fixed, and I'm varying across different choices of T double prime. But anyway, here's the picture. So the picture on the left is the same picture that I showed you a few slides ago, and then the picture on the right is them glued together. And so so we have the situation on the left, modulo that relation that I just told you, and that is isomorphic to the situation on the right. Wait, sorry, one more time.
The line under the black line, the math localized and isomorphism.
Yeah.
What did you say there?
Oh, yeah, right. So I was just trying to say, okay, so what I have in the orange above are like Skein Lasagna modules where I'm inputting links or inputting things. And I was just trying to denote like what things I'm inputting. So the first, we have the Skein Lasagna module of x1. And there I have, and I guess I should have put union signs, not parentheses, maybe, or not commas, maybe. But there I'm inputting like a T prime and a T double prime. And the second one, I'm inputting a T double prime and a T triple prime. And then I get over here, when I glue it together, I get a Skein Lasagna module with respect to the link, which is T prime and T triple prime. So that T double prime goes away because it's, yeah. Oh, yeah, the little caret. Yeah, sorry, that was confusing. The caret has no like mathematical meaning. It just means like put in there. I'll think of it. Maybe I'll do an arrow next time or something. Yeah.
Are you going to talk about how you, all right, so I can see that this gives you a map in one direction. Can you talk about how you can with lines or connect it?
I wasn't really planning, I wasn't planning on elaborating any further than what I did just now. But maybe we could talk about that later. But
You have to say you have your lasagna balls outside of where intersection is, then that's okay. So then we're worrying about cutting through the lasagna.
that's right, yeah. So the question is like, so Gordon was saying so that the problem is where are the lasagna balls? And I also meant to say, sorry. So here, when I'm saying lasagna filling, like I didn't draw any input balls or links or anything. That's totally a schematic. But yeah, that's one thing you have to worry about is when you have balls like just over here, I could have some input ball that's intersecting this Y2. And so in that situation, you need to know that you can always isotope them to either side. So that's part of what we're doing. But the point is, like what we're showing is that this relation we modded by is enough to fix any sort of problem that could come up, including that one that you just mentioned.
So you isotope the balls to either side and then you extra links maybe.
So we isotope the balls to each side. Yeah, okay. Yeah. So this is kind of the most technical I'm going to get. I'll talk a little bit more about the other stuff we do, but this is the worst of it. But sorry if you wanted more technical TLC, but I'm kidding. But any question, I'm going to move on to now we've glued two pieces, and I'm going to move on to self-gluing. So if you have any questions about this, now is the time. Cool. Okay, so now if we're thinking about trisections, I can apply the theorem I just wrote down to gluing 3 pieces together. So I have an x1 and x2, I glue along a y2, an x2 and an x3, I glue along a y2, and I get this like Pac-Man thing. So if I want to get a closed thing, I need to self-glue. And if I'm assuming my pieces are trisection piece, if they're all what they're supposed to be, then this y prime and y double prime are supposed to be 2 things that are diffeomorphic, so I can glue it together. So x is going to be the thing before I've self-glued, and then x bar is going to be now I've glued via this diffeomorphism. And so this process is fairly similar to that of the preceding theorem. By this process, I mean getting gluing theorem. In some ways it's similar, in some ways it's not. I'll say in which ways it's not. So we kind of have, so we basically break this up into 2 steps. One reason for doing this is, so we're like fixing a point set from the get-go. So at some point we have to deal with the fact that what if I have a different point set? What if my points move around? And so we could encode that into the definition of our category, but that caused some issues we didn't want to deal with. So instead, we're breaking this into 2 steps to kind of help with that. So what we first do is we define some kind of self-tensor product that's like extremely analogous to the tensor product that I showed you earlier. And then we show that this thing is isomorphic to the Skein Lasagna module of x bar where I've glued, but I take out a neighborhood of my surface with respect to this link P cross S1. That's made when I take out this neighborhood of this surface. And this part is very analogous to what I just talked about. Like in particular, this self-tensor product, like there is a relation in there, and the relation is very similar. It's kind of like before you glue, you could act by morphism here, or you could act by morphism here, but it shouldn't matter once you glue it together. So this part looks pretty similar. But then when we glue in the surface, this central surface back in, we have some additional things we need to worry about. So to recover the Skein Lasagna module of the closed form manifold, we need 2 additional relations. So here's the result. I'm taking this, which again, this is going to be massive, direct sum over all possible point sets of this Skein Lasagna module of x bar minus this neighborhood. Oh, yeah. Yeah, it just means that the link is the empty set, and that's okay. That's a possibility that you could have.
Take out the ball. We have the neighborhood of
Your definition had empty boundary and empty link, right?
Okay. Yeah, sorry. I didn't. Yeah, and I maybe should have been more explicit in my notation there. But yeah. Right. So So what do we need to mod out by to make this happen? So on the one hand, we need this braid relation, and this shows up in other works related to this. So for lasagna filling, you need it to be equivalent to its union some braid cross SI, where B is a braid in sigma cross I. And then you need this. This is kind of a bad picture, but basically you need, you could have your filling away from your surface, and then you could make your filling intersect your central surface, and so you need to allow for that possibility. And so you need a relation to take care of that. Sorry, I'm losing my voice. So once you mod out by those 2 things, then I finally constructed the lasagna, the Skein Lasagna module of my closed thing. Sigma is the central surface.
Sorry?
Sigma is the central surface of the trisection, which is also the boundary of those 3 manifolds.
In there.
Yeah. So like, right. So previously I have this thing where I have this like hole cut out, but once I put it back in, I could push my surface, through there, and so I need to account for that. Yeah.
The modding out by the braid is to deal with your fixed points maybe moving around?
Yes. Sorry. Yeah. Thank you. Yeah. So the question is modding out by the braid is dealing with the fixed points possibly moving around, yeah.
So just any action that, like anything, no matter what the braid word is, it doesn't matter.
Yeah, yeah.
Okay.
Yeah, I mean, again, these relations are what they need to be to make the theorems true in some sense. But so that's kind of where the story leaves off right now. So we're like I've said, this is very much continuing work. So this is where we would hope to head next. So that's TBD, concrete calculations. Maybe next time you hear me talk a year from now, I'll have something more to say here. But anyway, thanks.
Any questions for Sarah?
Well, how do you prove your math is
What was the question?
Sorry, the question is, how do I prove the map is onto, presuming that you're talking about this thing here? Yeah, sorry, my brain is, I was not prepared to talk about this, and so probably I'm not going to be able to come up with something intelligent to say right now, but I could tell you more about it later. Yeah. So the question is, I think, am I defining an invariant of a closed form manifold? With a trisection. Well, yeah, I guess the invariant of the closed thing is not new. That's supposed to be the Skein, the normal Skein Lasagna module. But in order to figure out how to get there from building a trisection, we define this like new thing on these like cornered pieces so that we can track through. Sorry? Yeah, hopefully the result wouldn't depend on the trisection. Yeah.
Is there any reason to look at multi-sections? Like, do you get simpler pieces if you do that? Does it mess anything up?
Yeah, so the question is, what about multi-sections? And I mean, yeah, so this would be something that maybe would think about going forward. I mean, what I would like to do, what I want to do first, I have no idea if this is feasible or not, but I really want to look at CP2 because the trisection of CP2 is just 3 4-balls, so that seems nice. So that is maybe going to be the first thing we look at, either that or S2 cross S2 because we know what the answer is, so we like calculating things where we know what the right answer should be. But so those would kind of be first steps. But then, yeah, like if we were successful, then, because I think probably anything we're doing, there's nothing special about trisections here, so then if we were able to do something with those, then yeah, maybe in general, like it might be, the more pieces you have, the better, the simpler the things are, and so maybe, yeah. Jeff.
So maybe the simplest thing would be to recover the calculation from S4 from the calculation of B4 using a theta 0 trisection.
Yeah, that's true.
Do you expect to be able to glue on 3 balls? By gluing on 3 balls might be simple enough that you can do that, or?
Yeah, I mean, I guess I don't know if I expect anything right now, but yeah, I mean, yeah, what I would like to do is work in, like, I have these lasagna fillings and do some kind of bridge trisection of them and like, yeah, but I think that, I don't know that we're like far enough in that process yet to be able to like claim that I think anything should or should not happen. Like what is?
I mean, there is you stated the results for the
Yeah, so for a 4-ball, the Skein Lasagna module of a 4-ball with the link in the boundary just is the Khovanov-Rozansky homology of that link in the S4. And that's not like, that's by construction. That wasn't like proven.
So maybe when you take 2 links and you identify different things, maybe it's not, if you know how, if, you just go through the proof of the glue and it's
Yeah. Yeah, one other thing, I have no idea like if this, how this will work or if this will work at all.
At least
Oh.
we'll connect something.
Yeah, so there's this like, so Mike Willis has this paper about Khovanov-Rozansky homology in connect sums of S1 cross S2. So we're very interested in that because that's what these three manifolds are. So I'm not sure if that will end up fitting into what we're doing or not, but that's definitely something we're like going to look at. Mm-hmm.
Could you go back to the first definition of S of, I kind of lost track of what. Yeah,
This thing?
right here, this page. S of Y. So I'm trying to understand, I mean, suppose Y is 3 ball. Right. And then Y cross I is 4 ball. This is some, I mean, I'm not used to thinking categorically.
Me neither.
This is somehow different, but also the same as the Skein Lasagna model before. But it's thought of as a more, can you like elucidate a little bit what I'm confused about?
Yes and no. So there is, okay, so this, I can't justify, this has been told to me by people that do category, people like Paul Vedich who think about categories all the time. But somehow the right setup here is that if you're associating, like we're associating modules to 4-dimensional things. And so then the way the framework should work is that as you go down in dimension, the like type of thing gets higher. So the 3-manifold should have a category. And then another part of what we're trying to do is we would like to associate to the surface a 2 category, except that's not exactly working exactly the way we want, but we want some, so there's some kind of like way this should fit into each other for reasons that are maybe obvious to people that think about TQFTs all the time. And I don't know if I can say a whole lot about that, but yeah. So a lot of, yeah, I mean, if like me, you're new to this stuff, some of it might just seem like out of nowhere, but we are kind of following like schematics that have been used by people that do this kind of thing all the time.